How are you? All good? How's your weekend? So I enjoy India, of course, very much. And then yesterday I had a chance to visit the center of Hyderabad, and we visited some. Thanks to Professor Madhav, and he spent a whole day with me. Appreciate that. And then we went to see some palace. It's just a beautiful city, so a lot for me to learn. Thank you. And amazing video as well, where I can see a lot of potential development in India and in IITH as well. Congratulations to all. All right. So coming back to our lectures, particularly today, the lecture 3, I will cover about the newly direct strength method. They say newly developed, but actually for quite a few years already. But as a newly, because it hasn't been done yet. It's not 100%. You still have a lot of work to do. But basically, we can use that. And then officially that are now incorporated in AISI and also in standard. And then now it actually moved into the main part. And the effective width that you learned last week now is moved into appendix. I will talk mainly in AS and ZS 4600 because this is where I came from. I did a lot of research to incorporate my research to that. But as Professor Madhavan just mentioned, that AISI S100 specification and AIS and NZ 4600 very similar, probably 98%, because there are some reason that I shared with you before. So it's just slightly different in notation. However, equation probably exactly the same. Okay, so it's just for you to make sure that you're aware of that. All right, so before going to the detail, I'm just quickly go to what we will cover today. So I'm going to talk a little bit of the background and where's how's DSM start with, and then I'm talk about the general methodology, how we're going to use direct strength method, and then just keep sharing with you what's going on in terms of direct strength method. We at Sydney Uni we play quite a key roles in developing direct strength method, particularly for the area for the shear combined action, and that's totally developed in Sydney Uni. And one of very important things that make the direct strength method possible or can be done is the what I say is the invention or the founder of distortional buckling. Have you heard about that? Yeah, we're going to talk a lot. So Professor Gregory Hancock is a big inventor. He's the first one in the world to understand and give the definition of distortional buckling. It just happened mostly in thin wall or cold form steel. It may happen in hot rolled steel, but normally we don't see that. But in cold form steel, I see it's very common. So I will talk about that history later on, and just give you deeper insight about what's going on. Okay. Now, I will jump straight to this figure. I already introduced a little bit in our first lectures about the new innovative section. So those are, it's not new. They're all in market. So very popular in Australia, in New Zealand and Australia, of course, they're all in UK and New Zealand. So they make it very complex. Okay, so this is complex section. So I'm sure that the company make those sections not just for fun, right? There's some purpose behind it. So of course, as you can imagine, like in Australia, we use high strength steel. So that's why I make the section very thin. And normally it's, for purlin, it goes down to 1.2 or 1 millimeter thickness. And then if you imagine like 1 millimeter thickness with the 200 depth or 250 depth, it's very slender. Then it's easy to buckle. in any failure mode like local buckling, torsional buckling, or flexor torsional buckling, or any combination of those. So the way that they can improve that, because yield strength can't improve, right? Yield strength is already good, 600, 550. So if you thin the section and if you use effective width method, and then it just go up to 200 or something, 300, it's buckle. That's what we learned last time, right? So if we couldn't get the best benefit of high strength steel, why you make it very strong, but then its failure is maybe half of stress. The only way that they can improve is make buckling loads increasing by introduce those stiffener. So those stiffener will push up, not strength, but buckling. And the buckling, as you learned from the previous lecture, somehow play a role in the strength equation at the end. So at the end, you got an ultimate capacity of the section or the member that will be increased because the introduction of those stiffener. Now, when you did effective width method last week, right? Can you imagine how you're going to do that? All right. Now, I can't do, sorry. So it seems like it's impossible to use effective width method in those complex sections. So that's the motivation. And sometimes we can, if you spend day and days, and then I'm sure the accuracy is not that great because it's all based on some assumption. So that is the reason behind, or the motivation of the need that we need to find some more advanced way to design for those type of section. Okay. And the other thing is we need to do something with advanced analysis. Particularly nowadays, we talk about the final element analysis, all computer softwares and everything. So for those type of structure member, co-form or complex section, we need to do something related to advanced analysis to use that one. Okay. So that is what the driver behind that. So first, introduced or developed by Professor Schaefer and Professor Pickup in Cornell University. So on this one, I just give you a bit of information behind those professors. Right? So Professor Pickup is the student of Professor Winter, George Winter, the grandfather of effective width or co-form steel structure in AISI in America. And Professor Pickup is his student, PhD, and he followed that branch. And Professor Schaefer is another one. He's a student of Professor Pickup, and now is the guru or the leader in co-form steel in America. So when we talk about direct strength method, we talk about the work of Professor Schaefer and Professor Pickup. Right, and that is, as I explained to you, is just the other way, or to replace, or not to replace, it's just to give you another choice to use for instead of using effective width method. Now, for officially incorporated in the standard, so start from 2004, it included in the appendix. As you say, you imagine like if you introduce something new in a standard, normally it takes time to convince the communities about how it works, right? So Professor Schaefer start to include to convince the AISI committee, so they start to include the DSM in Appendix 1. It's just at the back of AISI S100 2004. And then later on, Professor Greg Hancock just created a new section in ASNZS 4600 in Australia, Chapter 7, just particularly focused on direct strength method. Right, so at that time, direct strength method is just developed for column and beam, simply those type of structural member. And that's it, 2004 and 2007. Right, so it's just very matching with my time. I'm very lucky, I'm fortunate. I'm probably got into this right time. So I started my PhD in 2006, and then I got a scholarship from BlueScope Skill, this is Tata BlueScope in here. And it's funded by them. So I came to Professor Hancock and say, what should I do for my PhD? So he said, people doing beam and column a lot, so why don't you do something in shear? People normally not focus in shear, right? Something new, and you're not going to step on the other toes, people, and then you do on your own one. I said, that's great, let's get started. So that's why I got in to do shear for 15 years from now with Professor Hancock. So we did a bit of work on that, so I will share with you what's going on that area. But then 2018, we incorporated our shear equation and shear works in IS and SS 4600 based on all my work and all my students later on. So we focus on that. And now this included the other stuff into the latest AS and ZS 4600, including all the member. Now you can cut the holes in the member. So it's very popular, right? It's not the steel, particularly for steel structure, normally you cut a hole in the web so to fit in all the aircon system like this one. You're not going to cut into air concrete, but for steel it's easy to cut the hole circular or slotted hole or any shape, and you can reduce the height of the ceiling. So now with that we can design now using direct strength method, and then the other area as well. So it's all included in the direct strength methods. So other than that, we still develop. As I said, it's not fully developed yet. So we need a lot of works on different areas. For example, like web crippling, we haven't touched. We're working on that. I have a couple of PhD students working on that. Hopefully we come up with some rules, design guidelines later on. We're getting there, almost done. And we're looking at the web crippling of hard section as well, and decking. Everything about those different type of section, how we're going to use direct strength method on those area. So it's keep going. You get excited on what's going on. Okay, so but just for now up to here, that's where we're up to. Right. So officially, 2006, Professor Schaeffer provided a guide for direct strength method. You can actually look it up, and then if you get a copy of that, that would be great, and it will explain to you all what's behind direct strength method. And then I got this one. I saw that, and then the beauty is he gave you a whole lot of example how to use direct strength method, so it makes you easy to follow. Okay, so what's different? So direct strength method uses cross-section analysis, buckling analysis for cross-section. I will explain a bit later. But remember in last lecture, when we use effective width method, we don't treat the section as a whole, right? We split into element, lift and flange and web or whatever, and then we combine later. That's the effective width. However, direct strength method, we talk about the whole section analysis. So we click the button of the program, and then it gives you a local buckling, distortional buckling, or whatever of the cross section, the whole section. All right, so that is what's different. And the important thing is give you the guideline for designing complex section. That's what I just mentioned earlier. So it's help you to design that more easily. And in general, it's more accurately. That is what the purpose. And I will show you later how advanced it is. It's instead of page by pages, using to do all the painful calculation about iteration, then what you do is one equation. Yeah. Two steps. One is using software, and then using one equation, then you got all what you want. Okay? So I will talk about it later. Now, as I explained a little bit before, the thought, the initial thinking about how the direct strand method was developed is the distortional buckling. It's actually the main thing that make the DSM possible, right? So back into years ago, probably in years 80 something, Professor Hancock conducted a very big test on purlin on the roof. The purlin system, Z section and C section underneath the decking, right? So that is what he wants to test in here. So showing you, this is the vacuum test, a huge vacuum test. So everyone knows that when we want to test the roofing system, we have to build a vacuum test, right? And then and we suck the air, and then it's similar like how it works in the practice where the roof subject to wind load or the other load. So you can see that huge vacuum test. The height here is about 5 meters. So that is the roof where we put it vertically. And there's 3 spans. And each span is 7 meters. So the long here is 20 meter length, and then 5 meter high. And this is the cross section where we cut, and you can see this is the roof, and this is purlin. So this is purlin. We put it this way, and we suck the air, and then we can simulate the behavior of the purlin system, as you can see here. So based on those vacuum tests, we developed the table for design for BlueScope steel in Australia. So when you look up the design table for purlin system in Australia, is actually based on those data we developed, we tested in Sydney Uni for many years ago. Okay. Now, this failure mode, this is local buckling. You can see it's hard to see, but I zoom it up. You can see this. So it's sucked in, so the bottom flange in compression. So it's buckled in local buckling. That's easy. So this is, do you remember the one that we talked last time? That is the raw bridging. That's the way that we make in Australia. But in here, you make the rod, right? The steel bar to make it a lateral restraint. So it's a similar way to do it, just to provide the lateral restraint in the middle of the span of the purlins. Okay, so this is the failure mode that you look at for local buckling. And interestingly, one of the figure that I think Professor Greg Hancock told me that this is I like the best. It shows you everything, not everything, but every single mode in here. First is, you can see that's local buckling. Okay? And here, distortional buckling. Oh, everyone familiar with distortional buckling? If you're working on cold form steel a little bit, but maybe for those who are not familiar with, I will explain more explicitly about distortional buckling. But this is the other failure mode that probably you just see that in cold form steel, not much in hot rolled steel. So this is distortional buckling, but you can see the way it's twisting and flexural. So that is another failure mode, is flexural torsional buckling. Okay. So imagine if you don't have this one, it's going to buckle outside and twist, right? This one. So if you're looking at the length of the member, it may buckle in the third mode, is flexural torsional buckling. All right. So basically, this figure tells you about 3 basic failure modes in cold form steel. That is local buckling, flexural torsional buckling, and distortional buckling. Okay, so importantly that you understand. So in general, the direct strength method will give you equation to determine those three strengths. And what you do is just compare all of them. Which one is smallest, it will govern your design. So it's very simple. Okay. Now, before moving to next slide, any question on everyone clear or unclear about this? Very important to understand the behavior first, and we move on the calculation and the design. Okay. Good.
Sometimes
yes.
Mixed of two modes of variance. Sometimes remember that may be mixed of any two modes of variance.
Oh, that's good. That's very good point. So that's what we call is interaction. So now in here, probably this figure tell you that buckle in maybe in combination between local buckling a little bit and flexor-torsional buckling. So in DSM equation, there's part that take into account the interaction. So that's a very good point. I will show you later, but that is definitely included in direct strength method that we can take into account the combination, or what we call in the other term is the interaction between those modes. Okay, not clearly 100% pure mode, but we can have some interaction as well. Good point, thanks. Now, distortion buckling, that's what I focus on, and that is what that's make me very proud because we Professor Hancock is one of is the one is actually the one is the inventor. I can say inventor is the one who gave the definition. All right, so just give you a bit of history on that. Distortional buckling actually not new until they got a bit of that long time in history for testing. You remember back into years ago, they tested and saw it, but they try not to understand that. Say no, it's not going to happen. So normally they restrain somehow to stop the flange going in and out, to force the member, just local buckling or the other mode, right? So they try not to understand, not to accept this one. Until Professor Hancock, he tested some section like that one, and he didn't restrain to make sure that the flange is open in and out. And then he found that mode in here. Okay, so that's the first one. And then he he wrote one of the famous paper in 796 about distortional buckling. That's one of the first paper on distortional buckling. And if you have time, you should read that paper. It's the most cited paper on cold form steel, I think, on that too. It's worth looking at that. So in 1976, you showed the paper by him, Hancock. All right, so to look at this one, you can see there's two failure modes. Look closely to the member here. You can see a little bit waving inside of the web and a little flange in here. A little bit waving. Have you seen clearly? Maybe not. Yeah, but that is local buckling, just happening in the member element. But in general, you can see that the flange and the lift just close a little bit in another halfway length. Okay, in the longer member. This is called distortional buckling. And that's what happened. You see that? The junction line between the lift and the flange just go in. And sometimes it's go out. Doesn't matter. It just, when it's buckled, it can go in or out. They're having the same critical load. So this is called distortional buckling. That's definition from Professor Hancock. Right. Now with the beam, this is the 4-point bending. This is one of the tests from my PhD student, testing coral aluminum channel section. And yes?
Can you go to the previous slide? So this information, can it be in other way?
Yeah, it can open now. Yes.
Both is possible with the similar condition?
Yes, right. Yes, it's so sensitive in imperfection. It's slightly, of course, you know, so the channel section never perfect. Normally it's open a little bit out or open in, it will guide whether it's come in and out. Okay? So it can be either in and out, but they will give you exactly the same critical load. Okay? But this one is just short one. But imagine you have double length. It's going to be in, but it's going to be another length. It's going to be out. So like this one. Okay? So this the whole curve. Okay? Good. Yes. Right, so I will explain later on. However, remember distortional buckling and local buckling are section capacity. It's nothing to do with length. Right, so as I explained to you, if you got double, it's going to go in and out and in and out. But it's the column still straight. Imagine you have to have a lateral restraint. Okay? And if you got triple time, it's going to go in and out and in and out in three halfway length. Okay, so it's just multiple halfway length.
So like, is it due to the inability of the link to take keep the outside and flange link to junction with the same thing?
So the lift play a very important role in the distortional buckling.
As like, I mean, underneath the channel we don't have this distortion buckling.
Yeah, if you don't, if you have unlift section, you don't have distortional buckling.
So then, is that the link which plays the role of
Distortional buckling. Yep. Yep.
then, like how will you how we say that lift is influencing or the like as you said geometric imperfection is influencing?
Geometric imperfection, it just influence the shape. It can open in and out, but not about the value. The critical stress is same. Okay? Good point. I will show you later on how a lift section, it doesn't have distortional buckling, and then it will show you in the graph later what we call a signature curve. I will talk about that later. Yes?
What if, say for example, this is 5 meter, right?
Mm-hmm.
If it is 10 meter,
Mm-hmm.
then you know you have first like this and then like this, right?
Yep.
So when suppose I keep knobbing at
Yes,
5 meter,
yes, yes, yeah.
5 meter, well, there is no deformation as such because it is changing sign.
Yep, yep.
So if I keep or not, will it be same or different?
All right, good question. If you put that one in, of course, it means that you eliminate the flexure torsional buckling. You push up the flexure torsional buckling up, and this one will come in. But if you don't have that, maybe the flexure torsional buckling will curve in, it will be smaller, and that one not going to happen. It's just flexure torsional buckling straight away. So depend on how you want to do it. But at the end, when you put a knocking or what, you just calculate three things, and which one is smallest, it will govern the design. Okay? Yep.
So in underneath the section also we have this waviness in the flanges. And we will lift the channels, like in lift channel also distortion buckling have the same waviness. Then how we say that in lift channel it is local buckling, I mean lift channel it is distortion buckling and underlift channel it is like normal local.
So the signature curve later on will tell you everything. Okay? So I think it's very good for you, but we jump a little bit ahead. All right, don't worry, I will talk a little bit later, very deeply. But just roughly before we move on, that one is the heart of the direct strength method is the signature curve. And then the signature curve will give you three distinct points. One is local buckling, distortion buckling, and then flexure torsion buckling. And if you design for whatever section you want, you put in the thin wall or program, you run it, and if the second point doesn't exist, so mean that section doesn't have distortional buckling. Okay, and then it will show you in the failure mode. Oh, good. Right, now it's a beam. Beam is a little bit different, right? It's just top one in compression, the bottom one is in tension, so nothing to do in this one. So you can see here on the top, it can buckle, and then the junction line will go up and down as the longer the halfway length. Okay. So you can see the halfway length from here to here somehow, and this one to explain to you, right? If it's long, it's going to go down and up and down. So it's another halfway length. So that's distortional buckling. Okay. So that's what I explained to you roughly about 3 failure modes. The first one here is my test when I did my PhD, where I test the channel section in bending. So this is channel, but when I test is I put it toe to toe, like this one, okay? And I put a strap on top of that. The spacing is quite small. And then we test it in bending. And it buckle, you can see, that is in local buckling. So this situation is similar to the one in the practice, where you have the purlin and you got the roof sitting on top. Right, so the roof sitting will be attached to your toe flange in a way like this one. And the roof sitting on top will help somehow just force our compression, purlin here to fail in local buckling. Okay, so that's how we test it. This one, yes. Sorry?
What is the purpose of the balance?
This one? So that's, we put a strap to connect between 2 channels. Yeah. So the purpose of those straps I explained to you before, we want to force our member here to fail in local buckling. And it's related to the situation in the practice where you put a roof sitting on top. And it's subject to downward loading, okay? Downward wind or snow or whatever, downward loading. Right, so but in the practice is sometimes your member here, your purlin can be subjected to uplift wind, blow it up, not just always going down, going up, right? So when it's blow up, and then our member now subject to different stress, right? The bottom flange now will be in compression. So this one, we turn it around. We test it. So in the practice, when it blow up, the wind blow up, there's nothing to stop or to restrain from the bottom flange. Then that might happen. Distortional buckling, okay? And the last one here is one of the famous photos from Professor Nick Traher in our lab in 40 years ago, maybe. And he tested the flexure torsional buckling, where we test very long beam without any large ratio, and it just go to a certain point in flexure torsional buckling. Right, so this is member capacity. So in terms of the halfway, you can see that's one big halfway. It's just one big halfway for flexure torsional buckling. Right, so now in the cold form steel, when you design a beam, yes?
What is the loading condition in that third one?
This one is simply supported at 2 ends.
And load is vertical?
The loading is one vertical load at the end. So you remember 40 years ago, maybe 50 years something, in our lab, we don't have actuator, we don't have fancy stuff like us now. So you remember at that, what he test, he put a 2 bucket and then he pulled the water and to apply the load. It's a very interesting figure, isn't it? But very, very fundamental figure. Because of that test, the flexure torsional buckling equation is famous worldwide now. I'm sure that not every, but you know, all the specification, or at least in US, in Australia and Europe, they use his equation for flexure torsional buckling. So when you look at that, it's all based on that test 50 years ago at Sydney Uni, okay? Very interesting. So at that time, he tests that one, but remember, he tests his I-beam. And he has to use aluminum, because aluminum is it's softer, and then the stiffness is 1/3, so easy to get a failure mode in flexure torsional buckling, rather than using steel beam. It's too big and too stiff. Okay, right. So that's sharing you the failure mode that we tested at Sydney Uni, and then it's showing you the behavior or the actual observation, how you observe, understand the behavior of different phylum mode. Okay. So as I mentioned, to answer your question before, those two phylum modes are sectional capacity. So when we talk about sectional capacity, we talk about the property of the section. It depends on that, not depend on the length. We don't have to worry about the length. So when we said that, it means that in the practice, for your design of the purlin, you have already provided enough lateral restraint. Okay, the raw bridging, you already provide enough, so it doesn't buckle in flexor-torsional buckling or member buckling, but they just go to the sectional capacity. Because this member is so thin, it can fail in local or distortional buckling. All right, so that is sectional capacity. And the last one is the member capacity. As I explained to you before, if you remove the raw bridging, somehow, because you want to save a little bit of cost, but you have to think about those carefully, whether you compensate a bit of strength, but you can save one raw bridging. So something like that. So that's the other aspect of the design. Okay, so as I mentioned before, because of the trend now is to use computerized computer program or software to analyze or to design. So for conform steel, we use finite strip method. Okay, I think it's suitable for finite strip because the nature of the thin section, and then it's the longer section, so it's very ideal for finite strip, not like finite element, right? So so Professor Hancock is against him. So he one of the first one to develop the thin wool program that I will introduce you separate in next lectures on the development of thin wool 2 using finite strip method. Okay, so talking about finite strip, probably we need another lecture or something just fully on finite strip, but just in here, I just give you a brief introduction on that. So finite strip developed, the first one in the first professor developed finite strip is Professor K.F. Chung. Have you heard about him? So he's one of the professor in Hong Kong. He's Hong Kong. He's from Hong Kong, but he spent all his life in Australia, in University of Adelaide, and he's the first one to develop finite strip method. He got a very famous book published in 76 or something. If you're interested, you can look it up and learn a bit about finite strip. And then later on, Professor Hancock using all the theory and developed for buckling and everything. So if you're interested in the theory and know how it works, so you can look up my names and Professor Hancock names, and we got a couple of publication on the theory of finite strip. And recently we developed some more advanced in the theory, where we include the localized loading analysis. We're using complex mathematics, and we use multiple series terms. So it's a little bit complicated on that area, on that space. So if you're interested, just let me know. I will send you some reference. But all of that is we use that theory to develop the thin wool 2 program that you're going to use for your next lecture or for direct strand methods. So in general, finite strip, we cut the channel section into a series of strips. And what we do here, we apply the stress. You can see that is the normal stress, and it's in bending, so that's why on the top is in compression and the bottom is in tension. And with finite strip, methods. We're using semi-analytical finite strip, where we're looking at one halfway length. All right. This is this is very simple because we use only one side function in the longitudinal displacement. So you can see the side curve, and this is halfway length of a side curve. So we have only one very simple side function, and this linear we're using in the transverse axis. So that's for the displacement, and that's how we come up with finite strip. So this is because why is useful in conform stability design, because it's so simple. You can it's not like a finite element, right? You need a bit of skill to build up models, and you have to understand to model accurately the boundary condition and loading and everything. You need a bit of skill to do that. However, in order to incorporate it in standard, we need simple way. So that is finite strip will give you a very simple set to do it. So what you do, you just build up section, click the button, and give you all the result. So that's how we do. Right. So this is the Thinkwell program. So by using that finite strip, and we already coding it and put in the program, and I'm sure that Professor Madhavan has sent you all the links. So have you tried to install that? Have a go with that? Okay. So if you have time today, please take a little bit of time, play around with that and see how, and then we can work together. Have fun tomorrow, okay? To play with that. Okay. So the Thinkwell 2 program, what it does a bit of thing. First is, very good thing is they give you properties of the section, mechanical property. So what you do, you just input the cross section, whatever section you think about, and you press the material property. It gives you everything. Ix and Iy, it gives you the Zx, Ze, Zy, that's what we learned last time. And importantly, is it gives you straight away the location of shear center, centroid. You don't have to worry about that, and it gives you Iw. It's this warping constant. Everything is just on one click. You don't have to go to a lengthy equation in the appendix of the standard. That's the other choice, okay? So that is the first thing. They give you the property of the section. And the second one, very important for the Rack-Strand method, is they will plot for you that signature curve. All right. So I mentioned about signature curve a couple of times, but you might ask me, what is signature curve? Where that name came from? So just back into the history. So signature curve is the name that Professor Greg Hancock gave for that. And then I think now in the world now, when you go to any conference, when they write a paper, they said the signature curve of that section is based on what I just told you, okay? So the reason why he said that this is signature curve, everyone, I'm sure that you have signature. Everyone has. So I'm pretty sure that no one has the same signature. You agree with me? No matter you have same names or whatever, but or even twin, or you have your own signature. So what does it mean to me or to you in terms of this one? So what Professor Hancock explained to me that every section like you, every section has its own property or its own behavior. So they need a signature. So how are we going to distinguish between this signature? So signature curve here will give you the differences between the behavior of the section in terms of buckling. Give you a different, okay. So that's just the story behind it. So this, when you click on the buttons analysis in the Thinkwell program, and it gives you this graph. So this graph showing you on the right hand side, sorry, in the horizontal axis, showing you the halfway length. And then this one, it gives you different, but at the end it's gonna be the same. It's gonna give you buckling stress, or it will give you load factor. They're all same, right? Load factor is mean that if you apply the initial load, whatever, and you just multiple with the load factor, you got a buckling load. Or buckling stress, you calculate, you back calculate from stress to load. It's very similar. So this is the buckling stress or buckling load. This is halfway length. Right. So I'm sure that probably most of you understand that, yeah. But many of my students, or my audience, when I give lectures on direct strain method, normally they will ask me straight away the question, what is halfway length? What is that related to the length? When we use the length of the member, it's so confusing. So I will explain to you a little bit later, and then hopefully you can have a clear definition. So this one gives you halfway length, okay? And this is the number. So it's go up to about 10,000 millimeters. It's 10 meter. And this is 100 is 100 meter depth. This is 100 meter halfway length, okay? So this is signal curve between the buckling stress versus with halfway length. So the first mode is when it goes down to the bottom, the first one on your left, and this one where we can determine the local buckling. All right, from that one, you can go back, you project to here, and you know exactly what is the buckling load or buckling stress. And what we call here is local buckling stress, okay. So remember, this is elastic buckling, right? It's similar to the one that we calculate in the effective width is FOC or M node. Right, so this is local buckling. And then it's longer, it's about 1,000 halfway length. It gives you distortional buckling mode. So it fell in different mode, it's changing. And when it's getting longer, you got the Euler equation. Right, flexural torsional buckling. So if you don't worry about the section, if you treat as a member, so this is elastic buckling curve that we learned, right, from the theory. That is the Euler equation. But when it's getting shorter, then the sectional capacity jump in. So it might fail in distortional buckling or local buckling when you move to the left, okay? So in the practice, what does it mean? If in here it's happened, if you got a long purlin without any bracing, then it's buckle in flexural torsional buckling. It's gonna be here. But then you start to put more raw bridging, then you stop that one from happening, it's going up. It gives me better. But then again, it's chopping down here because the distortional buckling come in, all right? The raw bridging doesn't help for distortional buckling because it's sectional capacity, all right? And then if you put enough raw bridging, if putting enough strap on the flange or the roof or whatever, you increase distortional buckling and this guy will come in. All right, yes?
The final curve is PCRT.
Sorry?
The final curve we get, is that PCRT value?
This is buckling. Yeah.
Is that PCRT value?
Yes, buckling load. Yeah, this is the other one, the last one.
No, that includes everything.
This is elastic buckling, yes, but the strength is different, okay? We talk about the strength later on. This is buckling, okay? So remember, I jump ahead a bit. The direct strain method is the equation where you need two input. One input is the yield, and one input is the buckling. All right, and then that will tell you everything. Okay, buckling is showing you the behavior. All right, and the yield is, and then everything is showing you the material side of that. And this equation is, it works, it will cover everything about the imperfection, residual stress, or whatever. So that equation will tell you. Okay?
Previously, we have calculated PCRT value here. So is that like?
That's equivalent to FOC.
Here from the curve, can
Yeah.
we able to take that like to the length how much it is. So can we take the exact KRE value from this also?
In here,
It's the same in the
yeah, you just pick up the local, the minimum point. It's where it buckle. The minimum point here.
not local, with the oilers.
Euler here, yeah.
So you say my
Yeah, you are absolutely right. If you have the length and you have the cross section, you just go up here and you get it. You don't need to go to the equation that we learned. Yeah, so two ways to do it. I think that's a really good point. You can check. All right, and I'm sure that you have a very similar answer or response. Okay, exactly. You got I remember 7 meter, right? The beam or column. You got cross section. You plug into here. And you can look it up, what is the buckling load, and I'm sure that when you check the equation, very similar, very close. Yes?
FOC, critical buckling stress. Is there a local buckling stress?
Which one, sorry? Is that good?
FOC, critical buckling stress.
Yes.
So in this case, it is equal to local buckling stress.
You asking that this local buckling stress is similar to that?
Depends upon the length of the...
Yes. Remember on the effective width, on that one, it has a little bit of interaction in that equation already. This is pure local buckling. Okay, so maybe it's slightly a little bit different because that one, in effective width method, you go straight into the strength equation. Yep. But this one, this is local buckling. But in the DSM equation, there's the interaction in that, so it come in. So this is pure one. Yep.
So usually,
Now, yep.
so like usually when we calculate for effective method, we take the flat like excluding the curve, we'll take the excluding the normal curve, we'll take the flat.
Yep.
Using d by d, the whole to be.
So we treat as a plate and local buckling of the plate.
But here when we calculate, usually when we calculate for any section, the flat, like the LCR value which we get from involve is less than the actual flat.
You mean in thin wood?
So here we
Yeah.
get the minimum point, we have the LCR value, halfway value.
Halfway value, yes, that's the local buckling.
Usually it will be less than the effective, like effective method we use flat, excluding the corner curves.
Remember this is pure local buckling, right? The flat width, the effective width, that is strength. It's a little bit different. It's different. Yes. So that is the ultimate strength. This is elastic buckling. Okay. So then that one you put in the strength equation, then you got a strength of the whole section. Okay. So the effective width that you're asking is that actually the ultimate strength already, because we take into account the post buckling, because it's working out to be effective. So that is post buckling. Remember the first one that we run through, the stress is distributed, so that is post buckling. It's a little bit higher than the critical stress. This is critical stress for local buckling, but that is local buckling is for the whole section. Okay, so you can see it's buckle in top here, and there's one as well. It's local buckling of that. We don't treat as one like in effective width method. You separate that into only one flight, and you play with it. Good.
So this halfway length, is it the element length or member length?
The member length. Okay, I will show it very clearly later. Next slide. Okay. Yes. Good. Right. So now next one, come back to to explain. So what does it mean from this figure to our actual length? Right. So this is what it is. All right. So showing you. This is the whole length, and you can see that is the number of local buckling along the member. I don't know how many of them, maybe 10 of them. Go up and down, go up and down. And the local buckling, it just occurs in the element. What I'm saying is in the element, you can see in the flange or in the web. Yeah, so for example, on the flange, you can see in here, it go up and down and up and down. But importantly, in this figure, that junction line is almost straight. It just happened in the flange or in the web. in the web. All right? You see that? So that in the web, you can see here, in, out. And the top, in, out, up, and up, down, right? So, but the junction line here is straight, the junction line is straight. So this is local buckling. Now, when you run this one, you can see that is halfway. Each of them has halfway length. Oh, so it's corresponding to here. See, halfway. So it means that in here, if our member here is 7,000 meters or something, if I'm using 200 millimeter depth, the halfway length is roughly 200 millimeter. So you can see here, roughly 200 millimeter. You clear now? Halfway length.
So that's what I was saying. When we use 200 as depth, and halfway length is nearly equal to. But usually when we do involve analysis, it will be that halfway length will be less than 200.
Yes, it's going to be a little bit here.
So like,
Yeah.
Why it is less than 200? Not like depth is 200. So why the value shows sometimes it shows 160, 170 also.
You mean on the left side? Halfway length? But when you got smaller than that, the stress is higher. We need a minimum point when it gets to the critical one. Okay? So normally when you push that one, it will fail and mean that it's go to the bottom here. That means that it's 200. Okay. And then later on, you might play with that, put a little bit of stiffener, then it might change a little bit of halfway length. Maybe it's 220 or something. Or not 200. That's good. That's good practice for you to play and understand. Okay. So that is 200 now. Everyone got it? Right. So this is the second mode. This can happen where you look. Yeah. Imagine that upside down, and you got a wind uplift, and the flange can go up and down like this one with a halfway length a little bit longer. So this is what it is. Halfway length of this one. Get it? Now, then this one is halfway length, but it's a lot longer, maybe 5 times. So now it's about 1 meter. Then this one, showing you this one. This is a blue one. Get it? Yep, 1,000. So this is about 5 times of this one. And then when you look at the halfway length, it's going to be like this one. Right? So that's second mode. Right? So you understand now where it came from. Now the last one is the other one, elastic buckling. The whole section will buckle sideways and twist because it's subjected to all the buckling, elastic buckling of the whole section. Right, so that is somewhere in here. And that will answer your question, depend on the length. The halfway length will go up and down. The longer it is, the lower buckling load it is, right? Now, back into the practice. When you design that, we start from this one. Very long, you design that, no good. What you're going to do next? Put one row of bridging in the middle. So what happens when you put one in the middle? You reduce half. The length, you reduce half. It's maybe up here somewhere. But you compare this one, it's still flexor torsional buckling. You put another one, it go up here. Yeah. So now no problem with flexor torsional buckling, but then that guy come in. All right, now good. So what you're going to do, put a strap on something, on top or roof decking, you move that one out. And that one come in. So this one's nothing you can help. You can have, then make the section complex. You're going to push that one out. All right, so that's why we need to improve the section complexity. So that's why I will talk about next example. So this is exactly the same dimension, but it's just slightly different in the geometry. So this is a patent of Professor Hancock and BlueScope Steel in Australia, where they make this section, this is called super purlin or super C. So in terms of manufacturing this one, it's not that hard, right? When you feed the point into the roller system, then you just fold a little bit in here. And then you make the section more complex. but then it's give you a little bit of, not a little bit, a lot help. So now, before I'm going to the detail or showing you the value, can you tell me what is the purpose of those one? I'm sure that I'm telling you already, all right? It's help. So what the purpose of those one? Yes?
Stiffness, it increases the stiffness.
Yes, and in other words, is increasing buckling capacity.
Reducing the half wear.
That's another one. Yes, good.
Reducing the flat bit ratio,
Yes, good point. Yes.
thickness ratio.
But in particular, those one in the web, what is that? You're right. Yeah, it helping a lot in local buckling. Yes. Now you know that this local buckling, because it buckle in and out, those guys will help. So that is for web. Now with the lift, it's not straight. It's go there and there. Now, what lift helps? Think about distortional buckling, right? It's up and down, and the lift play a very important role, as you pointed out before, into the behavior. So if you fold this lift in here, you mean that you give a stiffer lift, and then it will help for distortional buckling. All right? So it means that it's helping. So in that particular cross section, it actually help local buckling and distortional buckling. So in order to help you to understand a little more clearer, I just plot two of them on top of each other to see what's happened. You can see here, this is plane section, this is super section. So what happened? The local buckling going up. And the distortional buckling, you can see the lip going up, and because of that folded lip, that actually put that one here. See how much that pushing up. So when you run this one by introducing only a little bit of that section, and it's increased about 15% capacity of buckling. Okay, we're not talking about strength now. We're just talking about buckling capacity. It's going up about 15%. Right. So as an engineer now, we play around with optimization of the cross section. What is the best? Right. We don't want to make something very stiff on the lift, but then this one is planned, is no good. Because you have this one, but you don't have this one. So it just fell in local buckling. Doesn't matter about you make a lot stiffer in the lip, something. Or the other way around, if you make very strong in the web, and then something in here. So a balance playing problem, okay? Interestingly, you can see those curves are matching. So what does it mean?
After distortion, we have lower capacity.
Moment capacity, yes. So it doesn't matter a little bit changing in the stiffener because it doesn't change IX or IY a lot, right? Then no problem with the flexure torsional buckling. So in this case, you can see that helping sectional capacity, but not really flexure torsional buckling. Flexure torsional buckling, the only way that you have is provide more lateral strength to have that. But the sectional capacity you can make the section more complex that you want. Okay? Get it? Good. So I'm sure that you understand now. This is halfway length. You see that? So I put that one. The spacing is just not randomly. I have to calculate the local buckling halfway length, and I have to put the distance here smaller than the halfway length of local buckling. So I forced that section to fail in local buckling. Okay, so this is why I did the test in local buckling a long time ago. And this one, we don't have the strap. However, you can see the yellow thing in here is lateral restraint. When we did the test, we connect them and attach in only junction here. And then we stop that one from flexure torsional buckling. So this one, we force our section to fail in distortional buckling. So the way that we do that, we're trying to isolate the failure mode. Okay, good. Right, so this is the heart of direct strength method. So Professor Ben Schaeffer and Professor Pickup, at that time, I think in 1998, so he collected all the testing data from all around the world. So you got thousands of testing data, and he plugged into that very important figure, and that is where direct strength curve come in. All right. So he proposed two curves in here. One is strength that is for distortional buckling strength, and local buckling in here. Okay. Now, this is important and interesting. This will answer your question. Is about the interaction. Look, this one is pure local buckling. However, why there's a few of dots below that, and a lot of dots upper that. But when we do calibration, of course, we fit in the mean, in the middle, right? So there's variation in here. Of course, that's why we have to run the probability analysis, and we got a low factor, 5 factor coming in, okay? Or reliability, what is that? Is you know beta, right? Set the index, so we have to achieve the target 2.5 beta to calculate the reliability. So, but just talking in this one because of the interaction. Sometimes some tests, if you don't have the restraint, and it might fail in a little bit of local buckling, a little bit of distortional buckling, and that's dropped a little bit down to the pure curve. But not all of them, right? It's randomly you have some section that have some interaction. So it brings down the data a little bit down. There's a lot of research on interaction, particularly between local buckling and distortional buckling. You read the research on from Professor Dina Kamotin from Portugal and Professor Ben Yang from University of Hong Kong. They did a lot of work on interaction between local buckling and distortional buckling. And for local buckling, the direct strength method or direct strength equation already cover. I'll talk about that later on. Already cover the interaction between the local buckling and flexural torsional buckling. So in the equation, we take into account that one. But the interaction between the local buckling and distortional buckling, at the moment, we don't include it in the effect of that. We're still using that one, even though it's a little bit unconservative, but we have a little bit, not a little bit, we have a lot of debate and talk about that. And then Professor Ben Schaeffer say, yes, we think about that. However, the chance for that section is is rare, right? It's like, I don't know how many % of the section has having the interaction, but just a little bit, a small amount of those sections, then we have to bring the curve down. So you can see how much effect of that into industry. Thousands of pounds to build and design based on the curve, and you bring the curve down, it means that, you know, it's not economy, right? So you have to balance between the chance to get that and the chance to design that. But anyway, it doesn't mean that it's not safe. It's actually safe because it has been covered by the load factor already, the 5 factor. So it's no problem. Just give you some insight behind that. Right, so now I give you the flow chart. Or the step you want to have, right? Okay, yes, I think it's a good idea. Sorry, I'm so excited, so give you a lot of information, but I think it's good time now for 10 minutes of break, and then good time to chat if you want to have any question. Happy to talk. Thanks. Let's get back to our lectures. Okay. Right, so now we go through the procedure, step by step, how to use direct strength method. First is you compute the elastic local buckling, distortional buckling stresses. So it means that you just input your section into a program like oh, good. So you input the section into the program such as L02 or DSM or similar. The other program that you can use, GB-Tune, using general beam theory developed by Professor Dina Kamotim and his team. Different method, right? That program used GBT, and thin walls and CUFSM, we're using semi-analytical finite strip method. But at the end of the day, they will give you exactly the same answer, which is the signature curve. The local buckling, distortional buckling, and flexor-torsional buckling. Right, so that's where is elastic buckling. Remember back into what we learned, that is FOC, that is buckling load. The other side, you calculate the section capacity. So My is a yield, right? Yield moment. Okay, so you have a cross section, and you can calculate using structural mechanics, and you can work it out My. Easy, right? ZF times with Y. Now, from that, then you calculate the strength. Remember two things. This is elastic buckling, but this is the strength, but the strength in local buckling and the strength in distortional buckling. Right. Now, confusing about strength and elastic buckling? Anyone? So, elastic buckling is, in theory, very perfect, right? It buckle. Buckling analysis. But this is the strength, local strength. It means that in the practice, as you remember, in the effective whip method, right? The local buckling has a little bit of improvement because of post-buckling. Or maybe it does a little bit down because of imperfection or residual stress. And that will affect the strength. Similarly, we can calculate the same, the strength of the member in local buckling and the strength in distortional buckling. And the strength here, the equation will cover all what we talk about, all the residual stress, imperfection, post-buckling, and everything is built in strength in here. And then we calculate inelastic lateral brace buckling strength. I will show you later. And then at the end, you compare which one is the smaller. So this is the member capacity, and this is the distortional buckling or this local buckling. So this is member capacity. This is sectional capacity. This is member capacity. And then we, at the end, we calculate which one is the smallest one. Yes?
That one is actually elastic.
This one?
No, right side.
This one?
Yeah.
This one, isn't it?
Yes.
This one is the local buckling and distortional buckling strength.
It's written like elastic.
Sorry. I misunderstood. Sorry. Strength is here. Sorry. Okay, so my way. So forget about what I just talked about. All right, thank you for that. So actually, sorry, this is from signature curve. From that one, you can work it out the local buckling moment, M critical or P critical, right? From stress to calculate. Very simple time would, thank you for that one. I just, my head just go around. So from that, you calculate the strength. This is the strength, okay? The local buckling and distortional buckling strength. And that strength is already cover all the imperfection, residual stress, it's real strength. It's what you test in the practice. And from that, you have two of them, and you have the member capacity, and then you calculate which one is smallest one. So, this one is not new. This one is not direct strength method. This one based on the traditional equation from standard. That is what we get. Member capacity is not new in direct strength method. It just adopt from effective width, but this is new. So you calculate strength, then you calculate the distortional and local buckling strength, and you compare those three of them and get the lesser, the smallest one, and that will control or govern your design. Okay. So first is we calculate the inelastic buckling. That is this one, the member capacity, right? So as I mentioned before, it's not new. It's just based on FOC, remember? And then all that we calculate based on the equation. You can back calculate and you get the PC. So you have two ways to do it. As I mentioned to your question, you can use FOX and FOY or FOXZ or something we did. Remember in the example, we choose a lesser one and that is the buckling load. Or you can get directly from here. That is the FOC, buckling load. And then from that, you just put in the equation from the standard, then you get the strength. That's not new. So this is the equation from Australian standard depending on how slender our equation it is. So you can see here, if MO is the elastic buckling greater than 2.748 U moment of a member of a section, then what's going on? You can see there's no buckling in here because the buckling load is too high. Buckling moment is too high. So what does it mean? Is our member capacity is equal to yield. It's getting to maximum, okay? So in this term, what does it mean to us is we provide enough lateral strength. It means that when you don't have, so for example, you got 7 meters and you don't have anything in the middle, then M node will be very small. And then you put one row bracing, that M node will going up. You have 2 or 3 or whatever, that one will go up. Until that's greater than this number, it means that no problem with member capacity. So I think this is where you need to stop. You don't need to provide more because you already officially provide enough. Yes?
This M node is based on effectivity. How to calculate M node?
M node, there's equation on in the standard. So that's basic Thai related back to the equation from Professor Nick Chaher. It's famous equation that I told you about. So that is based on that.
And that equation will be having some sectional property things.
Yes, some IX and some I will show you later. There's some, yeah. So I'm sure that in Horo still you have the same. M node exactly the same.
Okay, so no reduction of any width or something, just use the whole section properties.
Yes. We use the whole section capacity. Okay. So that's not new, as I mentioned. This is just based on traditional, based on very theoretical background from Professor Nick Chaher. I'm not sure about Indian standard, what equation you use. Maybe you can show me later. But in Australia, we based on the work from Professor Nick Chaher a long time ago. All right, so in the middle range in here is when buckling come into play, okay? But not really purely flexure torsional buckling, elastic buckling. There's some somewhere in between. So what we call that is the inelastic buckling, right? And then the one in here, which means that when you got 7 meter and no buckling, no lateral restraint, so M naught is very small, then it's probably close to the theory through elastic buckling moment. So it means that in this one, very slender. So depend on the range, then you have different capacity. Remember, this is member capacity, right? Nothing to do with section capacity. We'll talk about that later. Right. So this one, elastic buckling moment, you can find that in the standard. And this is U moment, of course, you can calculate easily. Just from that, you got 2 of them. Plug into those 3 equations where it sits. If it sits in here, then you're using that equation. Otherwise, you're going to use different equation in here. All right, straightforward. That is member capacity. Then you calculate elastic buckling. You calculate elastic local and distal buckling strength. Before that, you need to run signature curve. Then now we need to work it out that minimum point from signature curve. And from that minimum point, you can calculate MOD. Right. So that is the elastic distortional buckling moment. And then from that, you plug into that direct strength method equation for distortional buckling. Then you got MBD, that is distortional buckling strength. Different with distortional buckling stress moment in here. Okay? So this is elastic buckling moment, elastic distortional buckling moment, and this is distortional buckling strength. Okay? So you can see in here, our direct strength method equation has 2 inputs. One is elastic buckling, one is yield. Right, so then it can cover every region of that equation. And you can see here, if lambda d is smaller than this one, that number, it means that that one close to MD. It close to MY. What does it mean? So it means it's close to U moment, right? So there's no reduction because of distortional buckling. So it's all depending on this guy. Okay, so section capacity, section property, right? So we put that one in, and then we can calculate MBD straight away. All right, so, and lambda d is the slenderness based on that equation, my on MOD, and that you put that one in, you got MBD. Similarly, you calculate the other one, you move to the left, you get another local buckling minimum point, and that one, you can calculate MOL. Right? And MOL here is the elastic local buckling moment. And this is different with MBL. MBL is local buckling strength. Yes?
Local buckling we have MBL is equal to MBE. Local buckling.
Yep.
But there we have MY.
Yep.
Is that mean that distortion buckling and global buckling doesn't interact?
That's exactly right. Yeah. That's what I'm talking about. You're really good. You jump ahead. That's really good. So this is where what I want to tell you a little bit later, but your point very interesting. That is why we use MBE here, not MY, because we take into account the interaction. So if we have interaction, that MBE here will reducing, and that equation will cover the interaction. But when you remember MD, MY, because at the moment We maybe later on we do a lot of research, we do a lot of testing. We may find the interaction between the distortional buckling and flexor-torsional buckling. However, at the moment, we haven't seen any, or we've seen very small number. So the committees will set it up like this one. Yes.
In the beginning, you showed a picture, you used to connect the background with
At the beginning, for purling, yes.
So in that test, we told that it is about to go to control of since we have that restricted way to distort from. So that is interaction in that case.
In that case, we don't have interaction because if you look closer to the test setup, we always have the lateral strand in between to make sure that it doesn't buckle in flexor-torsional buckling. But we don't put a strap on the flange because we want to force that one into force the channel to fail in distortional buckling. That's why we don't have the interaction. That is very good topic, needing to have a bit of research on that, but we haven't got any update yet for that one. Hopefully, we see how we go. If we have a significant number of tests that show interaction, then we need to revisit our equation. But so far, it's still, we're still using this one. Good point. So that actually covers the interaction, right? It's not just about pure mode, but it has some interaction. So with local buckling, we got interaction between the local and member capacity. You got MBE here, and then if you don't have enough lateral strand, then MBE here will be smaller than MY. And then when you plug into this equation, you got that MB here will be smaller because of the interaction. Okay. Right, simple. From thin wall, you got this, and you plug into that equation, you got this equation. You got that number. So that is second number that you want to look at. So that is 3 number, right? And then it's simple. You just choose the smallest one. How simple is that? So what happened is, just following up what we talked about, we still have a lot of work to do in the future, where the equation for combined action, like beam columns. So you might ask question about, if in the case where you got a column but it's subject to significant compression and bending. This is beam column. So what about DSM? How are we going to design for that? So it's actually done already by research by Dr. Torabian and Professor Schaeffer, and it's already been in the latest one, 2024 AISI. If you download it, you can have equation for that. And now we including new DSM for shear. And then unstiffen and stiffen. That already in the standard. So this is based on my work and my PhD student, Dr. S. Pham. So we already done is in the standard. And the other works that we already put in is when you design shear, but you cut the holes in the web, different size of the hole, different shape. It's very important. Remember, we got a purlin, you cut a hole close to the support, then shear problem. Then how you design for that? Then that rules will tell you how to do it. So it's part of my research and my student with Professor Hancock. And the third interesting research activity now is going on in Sydney Uni is we're looking at web crippling. Of course, you got a beam, you're looking at all good in member capacity. What happened at the end if the beam sitting on the other member or sitting in the between that one? So what is the web crippling? The crushing of the web or crushing of the member, that will be very interesting, and how to design for that. So we're looking at all the tests. We did a lot of tests and we come up with interesting proposal. So hopefully in next edition of the AISI, maybe not in the near future, but will be in the future. And hopefully in the next edition of Australian standard, we'll bring it in. So all research now is happening. We got a very good result and proposal, so we will share with you in the due course. Right, so this is all about, and then before we conclude the lectures, but not finished, okay? You feel free to ask any question, but I just wrap it up and give you some highlight about direct strain method. First, direct strain method using the same equation for flexure torsional buckling. The member capacity, as I mentioned, that's nothing new. So exactly the same. But then what news in here is we're using the whole section behavior. So in other words, is we're looking at the local buckling and distortional buckling of the whole section. We're not looking at the element. You're not split into flange and lip and web and separately calculate buckling. So what we do, we just use signature curve from Thinwood2 or from CUSM or GB2 or whatever program. You just got those 3 or 2 minimum points. Then you can calculate the local buckling and distortional buckling moment or load. Then you plug into the direct strain method equation. You got local and distortional buckling strength. And those 2 points. And then you got the one that you know already before, that's the member capacity. And what you do, compare those 3. Which one is smallest one? That will work in your design. And we already take into account the interaction between local buckling and flexure torsional buckling. That included in the direct strain method equation for local buckling. So far, we haven't got the evidence or the test that's showing the interaction between distortional buckling and flexure torsional buckling. So research still going. And remember, the other interaction is local buckling and distortional buckling. Sometimes you remember the cross section, when you click the button, yes, local buckling and distortional buckling, right? But some section, it has those one are very similar. Some section you can try, you play around. And the question here, if you have the question that has similar local buckling and distortional buckling, whether or not it has some interaction there. It might drop the capacity because of that interaction. We don't know yet. There are a few research done by the team from Portugal, led by Professor Kamotim and Professor Ben Yang from Hong Kong Polytech University. They propose some equation, but we're still looking on that one, okay? So that conclude my lecture 3 about the direct strain method, the introduction of that. So now the floor is open for discussion. Yes?
So when we do a finite strip analysis, there are certain cases where you will not get a specific minima for local distortion.
Yep.
So in that case, how will we account for that?
That's a really good question. I will share with you, we need to
One approach which we have seen, we need to run a constraint analysis, take the minimum of that, take that buckling after, then extrapolate with the term.
Yes, that's good. That's good thing. Just give you an example. In the design of shear, we run some section and there's no minimum. It's just going down and then going down. So your very good question is where are we going to pick up the local buckling? So it's very tough question, and then we have to make the decision here. So for us, we have to run a little bit more complicated. Is we run the actual buckling load of that section by using finite element or something like that similar to get the buckling load, accurate buckling load to put in the direct strain equation. Because the finite strip, the minimum point doesn't pick up.
In length, how will we decide if you go for a field?
So for shear, I mean, just give you an example of shear. You need to find out the actual length that you want to calculate. Of course, for shear, it's interesting problem on itself because, as you're aware, shear is a product of moment gradient. There's no such a shear problem in any design, right? If you got a beam or you run a structural analysis, whenever you have shear zone, it means that you have a moment gradient. If you have moment is constant, you don't have shear. So the only way that you can consider shear, pure shear, predominantly shear, is when the shear span up to, I think, 3 for hot rolled steel. For cold form steel, we test it up to 2.5, and then the bending come into play. So if you test the member with the shear span on the depth greater than 2, then you get to see the local buckling due to the bending. So it's very tricky. But you can, back into your question, you can design for bending, right, or compression. But normally bending, compression, you can have a clear load core or distortion buckling minimum point. However, if in some cases, if you can't do, because of the length and because of the barrel condition, you need to simulate exactly what you want. I have some very good question from one of our PhD students here when he tests compression, but only one halfway length of distortional buckling. So of course, because of the difference in barrel condition, the halfway length not like what we use or we run from finite strip, right? Because what finite strip we assume that is simply supported. It's very nice one halfway curve in here. But in the practice, because of the nature of the barrel condition, you want to test it. You have to make sure that you clamp it somehow and you test it. So the barrel condition at the end will affect your effective length. Instead of it has like very nice curve like this one. So like it's bent like this one is distortional buckling, right? It's open. So in the practice, it might be like this one, a little bit down here, and then it's bent like a little bit here, okay? Because of that barrel condition. But then it's okay. You can use exactly the same barrel condition as you have, and then you calculate, and then you validate or you calibrate your strength. Okay, so this is how you do in the practice. But in the design, you have to use the very the idealized simply supported to get the local buckling and distortional buckling. And for the beam, for example, of course, in the practice, you have the beam long like this one, right? And if you run finite element, depending on the barrel conditions, the buckling may be like this one, and then it's got that one. Sorry. I'm talking about this is the distortion of buckling maybe, and this one like this one. You agree with me? So that barrel condition here will affect the first halfway somehow, right? But because of the multiple halfway length, so we can sort of using this one as the pure distortional buckling, and we can plug into our distortional buckling equation. So everything will happen in the middle, and it fell in here, right? So it doesn't affect the whole the ultimate strength of the beam. Okay, so that's how we can make it simple for the design. Good question. Yep.
One more question.
You can ask more, don't worry.
So when we refer to American roll,
Yep.
so there is another expression given as elastic capacity due to pressure torsion. They have considered MP, plastic moment capacity.
Yep.
So in Australian code, I couldn't find out that expression.
Okay, so I think we do now in the latest one. Have you downloaded the latest one?
I'm not quite sure. My fundamental question is, can we go up to that limit?
Yes, we do. As I explained to you before, the work of Dr. Turabian and Professor Schaefer. So what happened is, you got, this is buckling, right? The retraction. So at the moment, you can see when it go up to here, the lambda, depend on local buckling or distortion rate, 0.673 or something, right? So you just put it 1. So it means that, we go up there. That's it. It's used moment, done. However, in the practice, we did a lot of tests. So actually up here. So it means that if you use that equation for those range, it's a little bit conservative. So at the moment, when you read the inelastic reserve capacity in the standard, Professor Schaefer and Dr. Schaefer proposed equation is already in standard. So it actually goes straight in here. So this is linear. And this is about, depends. So it's related to the plastic moment and U moment. There's an equation on that. You just look it up on that. I'll show you later. I got a Australian standard software, the soft copy, and I will pull it up for you later on to show you. Okay, so it's good.
So they don't have this separation down as well. They have only single equation, which goes beyond.
You mean this one?
Yes, similar for PN and
PN, yeah.
Before PN is equal to PNE, which is less than 0.5.
So that score is the inelastic reserve.
DSM code has only single equation, and at some point it goes beyond. So is that the same thing which you were saying?
Yeah, the same thing. It's.
But the equation is a single equation, but you say there's a dual curve, like one is down linear and another is curve.
This is the normal direction curve. Okay? This is nothing new with this. This is all here, what we learned. But from here to here, instead of using my, you're using a slightly different equation.
Here we have two properties, one is linear and another is curve.
Yep. This is not Euler, this is a strength curve. Yeah.
So let me take it left. It's a single curve only. It will extend.
Yeah, it's only one curve, but this one, it just limit here, lambda. Up to here, you need to use the current one, the strength curve. But from here to here, you use the elastic reserve equation. You get it? Okay. This one, the work called inelastic reserve capacity. If you do a little research on this area, you probably familiar with the method called the CFN, the continuous strength.
CS.
Yeah. So the famous work from Professor Leroy Garner. So he's the one who introduced that work, and you can find a lot of interesting stuff on that. Yes, strength hardening, similar to that, but it's different. CFS, CMA.
Yes.
Yeah. So just something for your interest. If you really in that area of research, and you look at where they came from. Okay. So those from John Hopkins, and then the CFS from Imperial College from Professor Leroy Gardner. Groups, teams. Okay. Yes, other question? This is an opportunity for you to ask about previous one as well, if you wish. I'm happy to answer any question. Yeah.
This would maintain, sir. I just want to give a quick presentation on our project showcase.
Oh, you want it?
Yes, I have. That's a presentation.
Okay.
Contribution to industrial.
Yeah, you just talk to the guys.
I want to discuss.
Yeah.
Any doubts you can ask, otherwise we have a small presentation with our platform sponsor.
One more question, okay.
So, the ongoing researches you mentioned about localized loading. Localized loading, designed for localized loading web crypto.
Yes, yeah.
So similarly, suppose we know the loading condition of a queue, uniformly distributed load, but the DSM which we have developed is actually corresponding to uniform moment.
Yeah.
So can we take that advantage in the design for DSM for specific loading cases?
Right. Okay. So again, you raise very interesting question as well. So for member capacity, we're using very simple side function because it's subject to the constant stress distribution, right? Normal stress or shear stress or whatever is constant along the member. But with localized loading, when you got something at the end and you put a very localized loading at the on the member, then the buckling is a lot more complicated, right? So we actually already developed our ThinWorld 2 to accommodate that complexity. So we introduced, and then you can use that in ThinWorld 2 to run that one. We use more complicated, complex theory in partnership where we're using multiple series term. Okay, so just something for you interesting. I explain to you what is that. So for your bending, you got a cross section here, right? You put a bending. So you bending here, right? So it's buckle like this one. Okay? Or the other way around, doesn't matter. All right, so this is 1/2 wavelength. All right, so that's what a side function is. All right. However, so this is side function. You remember in our equation, so you got n is the number of mode, right? The first mode, second mode, or whatever. Okay. But when you have a web crippling, as you say, if you got member, then you got a little bit of stress in here. Then you got a localized stress distributed in here. So it means that when you run finite strip, if you have one side curve, you can't pick that one up. Okay? This is the displacement function. So what we do, we develop the finite strip, but we extend more series term. So it means that n here, we're using sometimes 25 to pick it up. So now, what it means by 25? So it means that to get that deflection, right? So we have to add, that's it, number 2, that's it, number 3, that's it, number 4. So we have to add this one all together to get that displacement. Right, so now finite strip method is not simple, this one, but you have to add like 25 term, and each of component here, you have to balance, at the end you got that small displacement that can pick it up the localized loading. Okay, so that is what we did already in the ThinWorld 2 program, and then you actually can solve that problem for your localized loading. So it's possible now. It's already we already program it in the ThinWorld 2, so you actually can use that for localized loading. But this is just behind the theory how we get there.
So with this we will calculate elastic flux, right?
Yes.
So directly can we plug it into the existing DSM equation and get the strength?
That's really good question. I can tell you what to say. we can't directly now to use the current standard.
That also needs.
Yes. The reason why is it's a lot more complicated than the moment and bending. Because the moment and bending, you remember my or py, u moment or u load, very simple. You get the section modulus times with the equation that. However, the u load in localized loading, py for this case, is more complicated. We need a proper model, how to calculate py on that one. So to come up with the py for localized loading is a big problem on itself in that one. So we're getting there. We get a couple of papers, we get some model. You remember here, because like the channel section, I'm just drawing the web, and means you pushing the load in here, and it buckle, but it buckle and it can yield. And then the yield area is like this one. It's folding, but that's one. All right. And now, how we work it out? How we calculate the yielding py in this case? That is challenging. So we need to come up some simple model to do it, and that's where we are. So this is one problem, and we plug into the DSM equation. We need to probably have to change to make some adjustment about some factor, component like exponent maybe not 0.4, maybe slightly different. We don't know yet, so we're getting there. We'll give you an update later on, maybe hopefully in the next few months. We get a proposal already. I present a paper in Barcelona. I think some of you will go there. So hopefully once we get that one done, and we will make a proposal, make a ballot to AISI for committee soon. Okay. We will keep you updated. Yes?
Yesterday's Friday's morning, you have discussed about two key problems.
Mm-hmm.
In the first key problem, you have taken the effective section area as well as whole section area.
Yep.
How come without calculating the effective section area, the capacity could be obtained in the main problem? Because in the second problem, the yield resource is given as 450. They have asked to calculate the effective section modulus.
Yep. For the beam, is it? Yep.
The same thing is also applicable to beam 1 also.
Yeah.
Where you have taken whole section modulus.
So the example that I gave to you is for the effective width when we use Fy equal to U stress, 450. Right. So this one, the last example. But when we calculate the first one, we got the elastic modulus of that section, which is not fully stressed. So that's why we need Fn is 200 something, isn't it?
280.
Yep. Yep. So what I'm saying here, I don't want to waste your time, but you're going to do exactly the same like you did, but instead of 450, you're using 208, 13 or something, isn't it? Can't remember the number. The Fn, the critical stress. Yeah. Yeah, that's right. So you use exactly the same method, procedure, and then you can calculate the effective section modulus, and that is the final result that I gave to you. But I haven't done that calculation. I just done with the Fy equal to 450, just to show you how to calculate that. But you can do exactly the same to get that number. Okay? Yep. That is probably a very good tutorial question for you to do it. Okay? Good. Any other? Then I'm happy to give the floor for you. Thanks.
Here it's okay. Here it's okay. Okay.
We'll have a small talk by our platinum sponsor, Zindal Steel.
Yeah, hello everyone. I am from Jindal Steel. We have been asked for a very quick presentation. I am just showcasing our project. This is our capabilities. We are doing designing, fabrication, detailing and erection also. These are the softwares which we are using. The Stat Pro is for steel designing, the ETABS is for composite buildings, and then Tekla is for detailing, for preparation of shop drawings. This is one of our product, corrugated web beam. What we are doing here is we are making it curve, sinusoidal, so that the stiffness can be increased. These are the projects which we have done with steel, DLF downtown. The total number of floor was 2 basement plus G plus 9, and the total area is around 1.5 million square feet. This is our another project, Raheja Mindspace. This is also in steel. Then Eco Park, Hyderabad. I don't think it's clear actually. What we are doing here is we are encasing these columns into concrete so that the composite effect can be taken. This is another project, Embassy Tech Village in Bangalore. Total number of floors was G plus 9 and the 12 buildings are there totally. IISc Bangalore, the total quantum was 12,000 metric ton. This we have completed in around 12 months. This is AIMS in Himachal Pradesh. This is also in composite. AIMS Hospital, Avantipura. This is also in composite. Alphatum Towers, G plus 29 story building. On the top of it, complete infinite pool is there. So the loading are transferring on the composite construction, the composite structure only. This is Cyberthumb project in Noida. This is also in composite. Total number of floors are 2 basement G plus 55 story building. This ball is basically the bridge between these two buildings. This is M3M. This is also in composite. We have completed this project in 12 months. Multi-story car parking. This is also in composite. NICL corporate tower, office building. This is in Kolkata. The total number of floors are basement plus G plus 14 and the quantum was 4,000 metric ton. This is Fairmount Hotel, 5-star hotel in Mumbai, G plus 12 story. This is also in composite, but the slab we are doing it, we have done with a precast slab. This is Omax project, 2 basement plus G plus 4. The columns are composite. For the slab, we have used composite deck system, that is cold form. Windsor IT building, 2 basement plus G plus 14. The total completion time was 10 months. If you are doing the same building with RCC, then 3 years is required. The slab cycle of steel building is around 7 to 8 days. For RCC, it's about 21 to 24 days. So these steel buildings are quick and fast. This is data center, D+7 story. Orion commercial building, number of floors are 25. Building height is around 100 meter. The total quantum was 4600 metric ton. This is group 108, G+17 story building, 2 basement. Total height was around 80 meter, and the quantum is 5100 metric ton. This is Swazi NSP. This is a small project, but the quantum is around 1400 metric ton. This is our institutional building in Sonipat. This is also student canteen, sports complex. All are in steel. This is PM Museum we have made in Teen Murti Bhavan, New Delhi. This chakra is in steel, this one. These are some projects with corrugated web beam. You can see the corrugation over here. These are rafters and these are columns. What we are doing here is we are increasing the strength of the beam. These are the corrugated web beams. This is factory. Columns are corrugated web beams. Rafters are also corrugated web beams. These are the sheds. Thank you. Just showing. Elements of the one slide is not going. One slide is not. This one. I'll just elaborate this one. This is the basic element. These are the columns. What we are doing is we are encasing this